We shall now look at a new concept, namely adjoint of a square matrix. Let us first observe its presence in view of a numerical example. Consider the matrix capital A is equal to this is a 3 by 3 square matrix. Altogether, how many? There are 3 rows and 3 columns. Good. Let us first find the cofactors of all these elements according to the known symbolism C11. What do you mean by C11? The cofactor of the element in the 1/1th place, that is the first row, first column. According to the definition, it is -1 whole to the power of 1 plus 1 into, delete the row and column. What do you have? 0 minus 2. 0, 2, 1, 3. It is -1 whole power 1 plus 1 is -1 whole square, that is plus 1 into 0 minus 2 is minus 2. C11 is minus 2. Well, C12, what is that? -1 whole power 1 plus 2 into first row, second column. 9 plus 4, 13. So it is minus 13. C13, -1 whole power 1 plus 3, as it is lying in the place 1/3 place, that is the first row and third column. -1 whole power 1 plus 3 into, come on, first row, third column. You'll delete them. 3 minus 0 is 3. 1 plus 3 is 4. -1 whole power 4, 8 plus 1, so it is 3. Next, C21. Those cofactors of those elements of second row. Come on, C21 is -1 whole power 2 plus 1 into, delete second row and first column. 6 plus 1, 7. So it is -7. Just like that, C22. What is C22? You may have to remove second row and second column. Second row and second column. 3 minus 2 is 1. Hence the answer is 1. C23, that is second row, third column. Second row, third column. 1 plus 4, 5. So it is -5. So far we could have found the cofactors of those elements present in the first row and second row. Now let us make a move to deal with those elements of third row. C31, -1 whole power 3 plus 1. You may have to remove third row and first column. Remove them. 4 minus 0 is 4. So it is 4. C32, -1 whole power 3 plus 2. Third row, second column. 2 plus 3, 5. So the answer is -5. At the last place, -1 whole power 3 plus 3 into, come on, remove third row and third column. 0 minus 6 is -6. Hence it is -6. Well, my dear, the cofactors of all the elements are before us. Now, you try to form a matrix with all cofactors. That is the matrix obtained by replacing the elements of A by their cofactors, corresponding cofactors. Come on. First row, 1, 2, -1. Their cofactors are -2, -13, 3. -2, -13, 3. Second row, -7, 1, -5. Third row, 4, -5, -6. Well, my dear, what can you say about that matrix? That is the matrix obtained by replacing the original elements of A by their corresponding cofactors. Now, if you can find the transpose of this matrix, this is called adjoint of A, denoted by ADJ. But of course, it must be read as adjoint A. So, in what way can we define the adjoint of a square matrix? Adjoint of a square matrix is, of course, the matrix obtained by the transpose of the matrix obtained by replacing the elements of A by their corresponding cofactors. Isn't it? Well, let us try to construct that sentence. For any square matrix A, the transpose of the matrix obtained by replacing the elements of A by their corresponding cofactors the transpose of the matrix obtained by replacing the elements of A by their corresponding cofactors is called adjoint of A. Adjoint of A denoted by either this symbol or like this. This is what we can mean by adjoint A. Well, it has a particular symbolism also in the case of square matrices of the type 3 by 3 or 4 by 4. There is a simple order. What is the general symbolism that we usually use? We shall now look at that. If A is equal to A1 B1 C1, A2 B2 C2, A3 B3 C3, it is of course a 3 by 3 matrix whose elements are A1 B1 C1, A2 B2 C2, A3 B3 C3. Okay, and the cofactors of A1 B1 C1 etc B3 C3 are respectively denoted by A1 B1 C1 A2 B2 C2 A3 B3 C3. Then adjoint A is equal to replace the elements by cofactors. What happens? A1 B1 C1, A2 B2 C2, A3 B3 C3. And the transpose of that matrix. This is nothing but A1 A2 A3, B1 B2 B3, C1 C2 C3. That is of course adjoint A, and this is the way in which we generally denote adjoint A, and theoretically the cofactors of these elements which are represented by small letters are represented by the corresponding capital letters. This is what we mean by adjoint A, the symbolism to represent adjoint. Good. This is about adjoint A. Now, this is the time for us to look at one of the most standard and useful results of adjoint A, that is A into adjoint A is equal to det A into I, isn't it? That is the next famous result or next important result. Let us first have the statement of that result. For any square matrix A adjoint A into A is equal to A into adjoint A is equal to det A into I. This is the most important, most standard, most popular and useful result. For any square matrix, A into adjoint A is equal to adjoint A into A is equal to det A into I. Well, my dear, to prove it, we need all these things. That is why I have kept the matter like that only on the board. Now, presently, we wish to verify that result. Adjoint A into A is equal to A into adjoint A is equal to det A into I. Okay, let me start. A is equal to like this. And the cofactors of all these elements might be represented like this. Automatically, adjoint A will be like this. Now, with this symbolism only, I like to calculate A into adjoint A. What happens? Let me see. Okay, let us consider capital A and adjoint A according to the previous symbolism. Then you consider A into adjoint A is equal to, what is A? A1, B1, C1, A2, B2, C2, A3, B3, C3. What is adjoint A? A1, A2, A3, B1, B2, B3, C1, C2, C3. Look here. First row, first column, multiply A1, A1 plus B1, B1, C1, C1. 1, 1, 1, 1, 1, 1. Elements are of first row, cofactors are also of first row. Therefore, this particular product is det A, isn't it? Next, first row, second column. A1, A2 plus B1, B2 plus C1, C2 is nothing but 0. Elements are of first row, cofactors are of second row. So, sum of the products is surely 0, and in a similar fashion you will get here also 0, 0, second row, second column. A2, A2 plus B2, B2 plus C2, C2 and 0, 0, 0, A3, A3 plus B3, B3 plus C3, C3. And according to our knowledge of properties of cofactors, this is det A and the remaining are zeros, hence it is det A 0, 0, 0, det A 0, 0, 0, det A. Now we can have det A as a common factor from this matrix, and it can be written as det A into I, det A into I. So we could have seen that A into adjoint A is equal to det A into I, and absolutely in a similar fashion you will be in a position to say that adjoint A into A is also det A into I. So from this observation we declare that this is a correct statement. Therefore, for any square matrix A into adjoint A is equal to adjoint A into A is equal to det A into I. Good. Well, from this we have a beautiful property of adjoint A, and this leads us to know the invertibility of a matrix. Of course, well, before going to that, let us now learn some more properties about this. Now, we take interest in finding the determinant of adjoint A. What is det adjoint A? What is that? Let us now observe. Look here. We know that A into adjoint A is equal to det A into I. Suppose A is singular. Then it is a very easy matter to look at that to say that adjoint A is also singular. Let us first take in from the beginning itself, let det A not equal to 0. That is, A is non-singular. Now, we take determinant on both the sides. Determinant of A into adjoint A is equal to determinant of det A into I. Let me notice this as some B, A into B. That AB is nothing but det A into det B. Now you consider this as some K, a constant K, K into I. Determinant is K power n into det I. Into det I. Okay, where n is the order of the square matrix. Let me suppose that A is an n by n non-singular matrix. Well done. Therefore, det A into det adjoint A. Therefore, det adjoint A is equal to det A power n minus 1 into det I is 1. As det A is not equal to 0, I could have divided on both the sides by det A so that it becomes det adjoint A is det A power n minus 1. This is the beautiful character of adjoint A. Det adjoint A is det A power n minus 1.